I'm Claudia Felser. I'm giving the introduction to this famous speaker now for Mildred Dresselhaus Memorial Lecture. So I want to say a few words about Mildred, here is this thing which I have to use. Okay, sorry. So she was born in Brooklyn, New York in 1930. And we have seen eventually already a few of these pictures, and she went to the Hunter College to get her bachelor degrees, to University of Cambridge in Harvard to get her ME, and she was also at Chicago University, like our speaker today, to get her PhDs, and she went on to Cornell. At MIT, she became a professor, and later an institute professor, and I had to update Tony's values about her citation by a factor of 2. In 2 years, it was doubled, I have to say, by Google Scholar, so she has an 8 index of 206, so she's a real role model for the young generation. She is for sure was a member of the National Academy of Science, and I think she got this very famous National Medal of Science and the Kavli Prize. You saw a few of the pictures already, but it's worth to repeat it, because I think she's a real role model for women in science like me, and also for very young women. And she was here, as you can see, even a founding member of the advisory board of RACAM in 2007. And here is a picture of the first workshop of RACAM in 2009. You eventually saw it too. And you see, she belonged to this advisory members here who always come every year, and I was lucky. I was, I think, at least 5 times or 6 times at these workshops. And with an increasing number of attendees, as you can see, you see already a few faces which you have the opportunity to hear talks about also in these workshops, because you see we are all very big fans of RACAM, and like Millie was too. And here's a nice photo, and I left it in there even because these are Tony slides, I have to say, and I like, it's very nice. It's from her Kavli Prize ceremony. You see, Tony was invited and joined her for the ceremony in Oslo. And here's a typical picture, which especially for the young people, I have to say, the last evening is a dinner with a sheikh, and we all have the opportunity to take pictures with the sheikh, including also the speakers. And here's an example from 2014, with Mildred. And I took this also, I kept this photo because you saw Didi Sharma already, another face which comes regularly to these meetings, and here with young women in science. So Millie, we really miss you. So since you are not with us the last years, but we are very happy to have a very famous lecturer today, and this is Shirley Meng. I want to introduce her too. She got her PhD in advanced materials in an alliance between Singapore and MIT, and she got a bachelor degree before from the NTU University in Singapore. Then she joined as a postdoctoral scientist and later as a research scientist at MIT. Now it was followed by the Zabel Endowed Chair Professor in Energy Technology at the University of California, San Diego, and now she's a professor of molecular engineering at the Pritzker School of Molecular Engineering, and she also serves as a chief scientist of the Oregon National Lab Center for Energy Storage and Science. She is interested, as you will learn today, in designing better materials for energy storage, and she does it in a very manifold way. So she uses first principle theory to have a guided material discovery. She designs the material, and she does advanced characterization using electron, neutrons, and photon sources. She received a number of prestigious prizes and awards, including the Faraday Medal of the Royal Chemistry Society, the International Battery Association Research Award, and the Blavatnik Award for Young Scientists. So she's still a young scientist also, in this sense, very close to the young scientist being here today, and the Science Award, Electrochemistry by BASF and Volkswagen in 2014. She's also an elected fellow of the Electrochemical Society and the Materials Research Society, and she's an editor-in-chief in the Material Research Society journal, Energy and Sustainability. So I don't want to steal more time of her, but I think she's really a really very good candidate now to give the lecture, the Dressel House Memorial Lecture. So please join me with welcoming her.
For the kind introduction. First of all, I would really like to express my gratitude to Sir Tony for the kind invitation to come to this beautiful place. I have never been to UAE before, so I'm glad I start my journey exploring UAE from this place. Let me just first say, hopefully, that some of you get to travel to beautiful Chicago. This is the picture taken in August. In February, it will look a different color. The university has a long history of supporting groundbreaking research, and it was my honor after spending 12 years in University of California, San Diego, to join the Pritzker School of Molecular Engineering and serve as a chief scientist in the National Laboratory, which is 35 miles away from the campus. Let's all spend 1 second to think about Millie. In fact, I had quite a few interactions with Professor Dresselhaus. A story you have never heard is that in 2004, almost all the research funding from US Department of Energy was directed towards hydrogen research. And I was almost finishing my PhD in energy storage with lithium-ion batteries. And it was a time that I was really worried about the future of my own field and whether I will be able to find a job and then have a good career. So Millie, being a professor at MIT, has always an open door policy for any female scientist who would like to go to her and ask her for advice. Yeah, I still remember today, Millie asked me one question. So, what do you consider as success if you have a good career? And I told her, I really want to see my research result being implemented in the society within the next 1 or 2 decades. And Millie said, okay, don't do hydrogen. Stick with batteries. That is the best advice I have gotten. And of course, she explained to me why hydrogen might take a little bit longer time. Everybody knows she is a big supporter for hydrogen storage. The carbon nanotube she is pioneering in is one of the major research topics for hydrogen storage. But she really followed the principles that as a mentor for the young people, she put my interest first. She said, what is good for you? If you would like to see things you work on impact the world immediately, maybe come back to hydrogen later. So for that, I'm always grateful to Millie for giving me the best advice in my career. So as a chief scientist for the National Laboratory, I think first let me share with a few things, the vision for the future. I think it's very important to realize that electrification is the absolute, no doubt, the future for the society. All of us, in fact, you look at your home, if your vacuum cleaner, your scooter, your car, something is running on batteries. And let me first show you, each person, the electricity consumption is about 10,000 kilowatt hour per year per person in the United States. I haven't checked the UAE number. I think because the quality of life here is also quite good, I think it's at least close to that number. Each person, if you only have 0.1% of the daily electricity you are using is stored in batteries. You are using 10 kilowatt hour battery. That's about a scooter size, electric scooter size batteries. And if you count the 8.5 billion people, like what His Highness said this morning, the neighborhood will have 85 terawatt hour batteries. And just give you a reference point, lead-acid batteries and the lithium-ion batteries are the only two battery technology has more than 1 terawatt-hour production capacity per year. So we already have a gap, right? And for smartphones, smart tablets, all the things you use, lithium-ion batteries made a huge difference. And I will just tell you that in the future, you should be able to charge your batteries within 5 minutes. That's in the small batteries, in the cell phone and tablet, it will definitely happen. And in terms of the number of cars, many people think, especially the car companies, believe we are going to 2 billion cars or more. But I think otherwise, because many young people today cares about the environment. So we use car services like Lyft and Uber. I don't have a car in Chicago, by the way. That I believe that the car numbers are actually going to be reduced instead of increasing. So the total number of cars, even if 1 billion cars, all those become electric, let's just imagine the scenario. That means we will have 100 terawatt-hour. Last but not least, for the grid of the future, I think we haven't really talked about which is the storage technology to win. I think for hydro, for the solar thermal, and the hydrogen, all of those will come into play. I believe that this morning the talk for the hydrogen is extremely interesting, so that the battery people don't get super stressed out. We are very stressed out because everyone thinks that we are going to solve the problem for the grid of the future. If we are just the 1/3 of the solution, that's another 100 terawatt-hour. So today, after 30 years of commercialization of lithium-ion batteries, we are 1% down with what we will need for the total number of batteries that we need for deep decarbonization. So whoever think that we are falling behind the Asian countries, Japan, Korea, and China, think again. The rest of the 99% game is still on. And I truly believe that it is also not a zero-sum game. And in terms of the battery chemistry and the battery technologies, hopefully today you're going to see there are a variety of choices based on your country's needs and based on the abundance of the elements available in your local regions. We can make choices now. So if you look at the history of the batteries, okay, it's important to realize, because we always hear, oh, so sodium batteries is going to replace lithium. No, absolutely not. If you look at the history, since Sir Alexander Volta discovered the Volta pile, you are still using AA, AAA batteries that is based on the chemistry that is invented by Sir Alexander Volta. And the French scientist Planté for the lead acid is over 150, 160 years old. Lead acid occupies half of the world's total battery sales. What it tells us is that every time when a new battery chemistry is invented and successfully scaled, we don't replace the old one. We simply expand the applications. And because of lithium-ion, electric cars is a reality today. So what we really need to think about is that even Nobel Prize is given to Professor Whittingham, Professor Goodenough for intercalation chemistry. There are still new chemistry to be discovered so that we can unlock things you previously think not possible by otherwise. Right? So one good example I could say is that in the United States, we're not just doing drones, we're actually doing flying cars. It's called electric vertical landing taking off vehicles. And you're welcome to come to LA to take a test drive. I think you do have to sign kind of waiver if there's an accident happens. It's very early technology. And I would say that it's very, of course, the ultimate goal is that we enable energy storage at gigawatt-hour scale. So for all the chemists in the audience, I sincerely apologize on behalf of my field, because watt-hour is actually not a proper international unit. So 1 watt-hour is 3,600 joule. So when we talk about a gigawatt-hour, we're already telling about a terajoule. When we talk about a terawatt-hour, we are already talking about a petajoule. So the units has to be clearly recognized. And I apologize because it's actually a jargon in our field. We always use watt-hour because the solar work is actually kind of benchmarked with the power unit, watt. So the time unit for battery people typically is watt-hour. So when we're doing this gigawatt-hour scale, we have to recognize the smart nature of electric vehicles and trucks. So again, all the things we put in such long-haul trucks will become part of the grid because the batteries we design will have such robust cycle life, you can actually do dual-way communication with the grid. So while we are trying to solve the transportation problems, we are simultaneously addressing the grid issues, and then we have to think about how can we build batteries that make this kind of grid-to-vehicle connectivities become a reality. So let's now deep dive into the chemistry. So in the Science Magazine perspective, we wrote this perspective to tell the public that we really need to think batteries not as a black box, but as a complex living system, just like the human bodies. Okay, let me explain. So when you have your current cell phone, every time you charge your batteries, the lithium ions will travel from the transition metal oxide to graphite, and both are so-called intercalation chemistry, and that is what's given to Nobel laureates in 2019. And during this process, okay, because battery is a closed system, just look at your cell phone. No matter can go inside and come out during the operation. So you probably don't realize that every time you're charging your battery, you are making a mini chemical plant. You are actually transferring all the electrical energy into the chemical energy because the lithium in the lithium cobalt oxide is very stable. When you use the electricity to drive it to the graphite, lithiated graphite is extremely reactive. So you make these two very unstable materials, and that's where it can actually automatically release chemical energy. Where the lithium travel back to lithium cobalt oxide, that's where you got the electrons. So this closed system has to have 99.9 efficiencies in order for your device to work for 1,000 cycles. And this principle of the solid electrolyte interface, because the side reaction can actually produce this kind of solid layer between the liquid electrolyte and the active materials. And the concept was introduced in 1997 by Dr. Pellet. We didn't have any of the fancy microscope. We did not have a lot of the fancy tools. But he, at that time, from the first principle, he proved that this SEI, solid electrolyte interface, will be the ultimate determining factor for the life and the safety of the batteries. So in my career, I spend most of my time to understand the interfacial science between the electrode and the electrolyte. The interesting thing is that now we have to go for higher energy density. So we have to jump out of this comfort zone of intercalation. We have to go to alloying, like silicon, tin. We have to go for depositing metallic lithium, electrochemically deposit reactive metal that has never been done before. But if you want to have a high energy metal batteries, you have to enable the reversible electrode deposition of reactive metal. On the cathode side, we will have to move away from transition metal because cobalt and nickel, they are actually scarce resource. If we think about 8.5 billion people in the world, we must find ways to enable sulfur or ultimately oxygen. Oxygen is the ultimate source for electrons that people can utilize to make batteries. So when we move away from intercalation, everything we learned in the past 30 years about the solid electrolyte have to change. And those boxes are completely empty now because a lot of time we really don't know what is the interface, for example, between the lithiated silicon and the electrolyte. And I will also mention a few things about how you can actually change this electrolyte, because this electrolyte is called a carbonated electrolyte, extremely flammable, and the majority of your safety issue is actually caused by the flammability of this liquid electrolyte. So I will give a few examples. Before I do that, I just want to emphasize the dynamic nature of the battery materials. And I think there are quite a few young students sitting in the audience. You know, remember when you learn kinetics and transport classes, how painful it is? I'll tell you, in battery research, those classes will be actually useful, that you will actually utilize the equations to understand what is the ultimate rate capability, how fast you can transport. So when you are charging and discharging the batteries, lithium has to be transported from anode to cathode or cathode to anode. Therefore, there is a dynamic phenomena that the charge and the mass, they are both being transported between these two electrodes. So when we look at lithium ion, it's an ion with a finite size. When you do sodium, it's the same. When you do hydrogen, it's slightly different because hydrogen is very tiny. Okay, so when you move the ions between the electrodes, it's like the airplanes taking off and landing. Every time, the materials of the airplane body will experience pressure differences. When you go high in altitude, it's low pressure. When you come down to the ground, it's high pressure. So in the battery materials, when you shuffle the materials, there is volume change. Actually, by Argonne National Laboratory's synchrotron, you can examine the batteries while the battery is operating. You can see how the lattice parameters are changing, and sometimes it will go through a phase transformation, but this phase transformation will be reversible. So when you discharge the batteries, the lines will move back. So that's the level of what we do to examine the batteries, just like how human bodies are examined by X-rays and NMR because you want to figure out what is going wrong. So those kind of operando characterizations give us a lot of useful insights about what happened. And you can imagine if the strain in those intercalation materials is not well managed, you will have the failure that's caused by the mechanical degradation. So in the last, I would say, more than a decade, I want to just share here, I know Professor Claire Gray, I saw her picture just now in the image. I was extremely lucky as a junior professor being invited to join this EFRC called Energy Frontier Research Center. So in the US, we are actually encourage team science, but the good thing with the team science is that an assistant professor like me can spend time to develop characterization tool that are focusing on how I can capture all the degradation mechanism from particle level to electrode level, and then ultimately to batteries. And if you have a battery that only have 98% Coulombic efficiencies, your battery fail after 200 cycles. And that's the batteries made back in 1993 or 1994. So the power of compound interest rate is quite astonishing. As soon as you bring the efficiencies to 3.9, your batteries will cycle 1,000 cycles without any challenge. So I was very fortunate that with all the support from DOE, actually our second director, so Claire moved to Cambridge, and she couldn't continue to be the director. So Professor Wadingham kindly took over the center. And that's, our center ended with Professor Wadingham got Nobel Prize. Unfortunately, we still have to finish the center because in US, most of the center lifetime is 10 years. So in terms of the, let me not showing you this cartoon picture. I'll just show you the real transmission electron microscopy work. So I chose the tool called the scanning transition electron microscope. Actually, the aberration corrector STEM, back 12 years ago, it's a new tool for the scientists. And when we look at the materials under the microscope, these are not simulation. These are real microscopy image of the battery materials. In the zone axis, every bright spot you see is the column of transition metals that are arranged perfectly in the crystal. And the lithium, because lithium has no electron density, so lithium appears to be very dark. And these are the superhighway for lithium transport. After you expose the materials to very high voltage, there will be significant changes happen. And the one thing you see is this superhighway for the lithium become lightened up by those transition metal. And this is one of the first evidence to show the major degradation mechanism in the batteries actually are caused by a surface, extremely surface sensitive mechanism that where you have oxygen loss. You see the in the EOS, electron energy loss spectroscopy, oxygen K edge, the pre-peak disappear, and the transition metal, because the oxygen vacancy was generated, the transition metal start to move. And this, at that time, because if you shine an X-ray on this crystal, you cannot tell the difference by X-ray diffraction at all, because it only happens on the surface 4 to 5 atomic layer. So my student, Chris Fell, who's now super rich because he joined Tesla in 2012. It's always good to see the students do better than the professors, financially especially. So he actually proposed that all the cathode materials should have a surface coating to protect the surface of the cathode. So this is one of the first I would say, results to help industry to understand the degradation, and then the knowledge we generated was very well utilized in the industry. So last 30 years, the battery field actually managed to extend the cycle life by more than, I would say, 10 times. More than 30 times maybe, partly because of the result I show you. And we were able, in the same cell format, we tripled the energy density. You don't feel it because you watch YouTube, do TikTok, and do everything on your phone, so the battery drains very fast. However, we actually did improve the energy density a lot. And the cost came down thanks to our colleague in Asia, Japan, Korea, and China. And today, recycling of batteries is happening. And I would say, please do not throw away your lithium batteries because the lithium and the cobalt and the nickel should not go back to the landfill as the landfill waste. They are actually critical elements we should try to get back. So all the changes in the battery in the last 30 years were driven by the breakthroughs in material science and engineering. We replaced the cobalt with nickel, and now we're replacing those materials with iron and manganese-rich oxides. I will tell you today a good story about how we move from graphite to lithium metal. It's absolutely happening. And then for electrolyte, the last story I will share with you is how you can build a battery that if you put the scissor, cut through the batteries, the device will still work and no fires. Right? So the roadmap here is a roadmap established by Argonne National Laboratory. It's very good to look at by energy by weight. So think about the drones. You know, the more you go this direction, the battery is better for the flying. And the energy by volume. So the batteries for the phone, for the cars, you only have a fixed volume to work with. But the roadmap shows actually the commercialized ones are only here. Right? So there are chemistry that are actually allow us to double the energy density in the next few years. So I will show you today, no matter what you work on, you have to figure out how to make lithium metal a possible anode materials so that you can double or triple the energy density of today's batteries. So lithium metal batteries, nothing new, okay? Actually, this first graph is adopted from a science paper, 1976, the year I was born, by Professor Whittingham, okay? So he used a very thick block of lithium metal and the titanium disulfide as the cathode. You were saying, oh, why don't he use lithium cobalt oxide? Lithium cobalt oxide did not get invented until Professor Goodenough read Professor Whittingham's paper in 1976, right? So he didn't have choice, and all these very thick, millimeter thick lithium metal, once it's being cycled, it becomes pulverized and become very high surface area lithium, and that's where all the safety problem happens. So I will skip the 2 generation because this is what you are using today, and this is very close to commercialization. But back in 2016, we actually convinced the US Department of Energy to let us revisit a materials that was abandoned 50 years ago. Actually, we also managed to convince Professor Whittingham to be part of the team, right? Because now you have very high lithium containing cathode materials, we should be able to just use very thin, very thin seed layer of lithium metal, and then we can actually cycle the batteries. And just by eyeballing, you can see the volumetric energy density improvement. And this is easy said and difficult to do. Why? Okay, first of all, it is really not easy to look at lithium metal. Okay? So if you use a scanning electron microscope and you use the gallium ion beam to cut the lithium cross-section to observe the cross-section of a electrochemically deposited lithium, if you use gallium, gallium actually reacts with lithium at room temperature. So everything you see here in the first 2 columns, they're not the true morphology of lithium metal. They are the reaction product of lithium-gallium alloys. And a lot of the earlier measurement was not correct because of this interference from the characterization tool. However, I was very fortunate in UC San Diego. Many colleagues in the bioengineering department start to use cryogenic imaging techniques. And lithium metal does not go through phase transformation until below minus 186 degrees Celsius. So we can borrow the tools to look at the cross-section of the lithium at low temperature. And this kind of cryogenic techniques developed really exciting things for us to visualize lithium in the micron, and this is cryogenic TEM. You can look at the lithium at nanoscale. This is 5 nanometer scale bars. And even more exciting is we can do tomography with X-ray or, with electron. And this is the lithium metal that is completely surrounded by this solid electrolyte interface. So lithium metal itself is conductive. But this blue layers of SEI is insulating. So under the microscope, to be able to differentiate this gave us the first hint that a lot of the failure mechanisms in the lithium metal batteries is caused by this kind of what we call the electronically isolated lithium. So they cannot participate in the battery operation because they lost their connection to the electron, to the current collector. And TEM, of course, is being heavily criticized because the sample statistics is very poor. Because normally I have 1 million particles, but I only look at 1. So how do you know what you're looking at is representative? So because of the criticism, I asked my student Chen Chen, who's now a professor in Michigan State, to develop a chemistry-based method, which a lot of chemists here. It's called the titration gas chromatography. So the principle is very easy. All the lithium-containing compounds, they either dissolve or react with water to generate a methane gas or CO2 gas. Lithium metal is the only one will generate hydrogen. So it's a very simple concept. We see if we can use a chemical method to quantify how much of this dead lithium is generated. And the calibration was superb. This technique was very good. I think we should thank the people who does hydrogen research. The earlier measurement error for hydrogen is because they don't use high purity helium. So for this measurement, you have to use high purity helium in order to get the GC method robust. So in this work, we showcase in all the electrolyte we have investigated, all the efficiencies perfectly correlate with the amount of lithium, unreacted lithium, and it's not caused by this so-called SEI layer. And this finding, maybe to external people, it's not that meaningful because, so what? If you have a lot of dead lithium that being isolated by the SEI, that your battery cannot cycle 1,000 cycles. But for people in the battery field, I think we were able to translate the knowledge by a very effective engineering mitigation method. So because lithium is very soft, if we have a lot of dead lithium that's isolated, so let's try something mechanical, all right? So the goal is to set up an experimental tool to look at if you put a gentle stack pressure on the electrodes, does that impact the efficiency? And the result was astonishing, okay? Because at a very low pressure, the electrochemically deposited lithium are extremely porous. So we still don't have the full understanding about the lithium nucleation in the organic solvents. All we observe is that it's very, very porous. So if I show you the cross-section image, it's even more astonishing because these are exactly same condition with the only exception is the stack pressure is 350 kilopascal is about 3 atmosphere. These scale bars are the same. Can you see that when you have almost no pressure, the lithium is highly porous, so the cross-section becomes very thick, but when you go to the optimal pressure, you can actually deposit lithium that is very dense, almost like theoretical density lithium. And this is eventually the reason why the lithium metal batteries efficiency was improved very significantly. And we didn't make those batteries. In fact, the consortium, the national lab partners use this technique to put the pressure on. You can see the pressure, stack pressure with the container. They were able to improve the performance very, very significantly. So this is, I would say, a really interesting journey to see a brand new technology. When you start working on it, every cell failed very, very fast. And when we make good progress in terms of changing electrolyte, put the pressure on, you can see how the performance improvement can be achieved within a very short span of a few years. So the ultimate outcome is that it's no longer a dream, that it's possible to have 500 miles per charge of cars. And the challenge is that when people get this kind of mileage, they also want us to do fast charging in 6 minutes. I think we will take up on the challenge, but I think it will take another few years before we can deliver those kind of fast charging capabilities. So for the next part, I will then shift the gear to a new chemistry. I think this morning His Highness mentioned about my conversation about the sodium. Okay, so I have a philosophical reasons why we all should do sodium. So everybody knows if you have too much salt in your diet, you get high blood pressure. You're not happy. However, sodium is everywhere. So sodium is widely distributed, and sodium ashes actually has really high distributions in North America and many other places, right? So I think the key here, if you calculate the lithium available for electricity grid, we will simply turn lithium just like petroleum. It will become really, really critical, scarce commodity. So we have to develop alternative chemistry that can perform similar work, similar job as lithium to mitigate the supply chain strain of lithium. So let's look at the sodium. And I think, hydrogen, lithium, sodium, they're all group 1, right? We all think we know everything about these elements. In fact, if you look at the electrochemical potential, right? So lithium is the most electronegative one. Sodium is only about 300 millielectron volt above it. So maybe we will lose a little bit of the energy density. The cost is really low. The sodium ash, the cost for acquiring is less than 1/30, okay? Distribution is very wide. So let me show you what today. So sodium-ion batteries has already taken off. However, many of you do not have that product in your hand. You cannot buy it in the market, right? This is one of the challenges we are facing, is that majority of the manufacturers will only make sodium batteries for mobility or electric stationary storage. So for mobile devices, it's unlikely you will get the sodium batteries, right? However, I believe in the near future, if you buy electric mobilities from China, perhaps also from France, you will be able to see some sodium batteries. So sodium batteries, do we really do it because it's inferior for lithium? So I will show you an example here. So we are using here the sodium metal as the anode and the sodium chromium oxide as the cathode. And here I ramp the charge rate very high. 5C means 12 minutes charge discharge. 8C means 7 minutes charge discharge. So the first trial with the electrolyte I just taken from lithium, and then I switch the salt to sodium. Okay, it's not the best, right? In the new electrolyte, sodium batteries can enable 3 minutes or even 1.5 minutes fast charge and discharge. Yeah, some people were very confused. Hey, Professor Meng, I thought sodium is very big ions. It should be more sluggish. Yeah, but solid-state chemistry does not work like that. I think Sir Tony can also teach you the structure of sodium, solid state. Sodium is a bigger ion. So when we make the structure, sodium will establish a bigger channel. So the structure is usually more open. So sodium actually can diffuse very fast in the solid, right? So here we show everybody that sodium batteries is really ready for the prime time. And I have to say, without NSF, I would not be where I am today. The active work started from 2010 in my career award. And my student from Iran, Baharak, spent the entire PhD to enable this type of superb performances in sodium-ion batteries. And today, 2 of my former students are actually trying to commercialize this technology. For full disclosure, Professor Meng is a scientific advisor for them for the sodium battery. And if you want a sample of unit-grade batteries, you can contact me after the talk. So this is a quite exciting development. I think, of course, you know, we have global competition, but I think that it is a good thing for us to see if within less than 10 years, we'll be able to scale the technology to gigawatt hour or terawatt hour scale. Okay, the last part of my talk, the last story is really about solid state. So I will invite many of you come to Chicago to visit me. Maybe first Sir Tony can come later this year. I will let you cut these batteries, okay? So the true beauty of solid-state battery is that it's extremely abuse tolerance, and it is very, very safe to handle. Of course, we don't encourage customers to cut the batteries all the time. It's just a demonstration to show you the beauty of solid state, okay? And also there's a philosophical idea about solid state. If you look at around you, right, what are the structures that last for thousands of years? They're usually ceramics, they're usually solids, and they usually last for a long time. I mean, solid-state lighting, computer chips, all those solid-state devices, in my opinion, batteries will move towards solid state. And another very exciting things, I think for non-expert you probably don't realize, is that in the battery manufacturing, in the solid-state battery manufacturing, we can do a complete solvent-free dry electrode processing, which means we can cut down significantly the production time and the production cost. So remember, my job is to actually figure out how to do terawatt hour in the shortest time possible. So manufacturing innovation is extremely important for this line of research. So we are not just focusing on the chemistry, but also the processing of the solid-state batteries. And during the processing for solid-state devices, there's a lot of challenge. So I actually, last week, I was in Kolkata with my former postdoc, Dr. Abik Banerjee, who's now in the Kolkata TCG Crest, to work on the solid state. So when he was working with me, one of the most important thing that we wrote in this highly cited chemical review paper is to show people when you do powder processing and in the solid state, every time a void is there, you have additional interfaces. So anyone think that when I do solid state, I have less interface problems because I don't have to deal with liquid? They're wrong. In fact, you have a more challenging question is how can you engineer those void or avoid the void formation in your processing, because otherwise the impedance of the cell will go uncontrolled because you have a lot of, the void cannot transport iron. Remember, the ions need the solid electrolyte contact point to transport. So this is where fuel cell people will come in to help us to solve the problem together, because the triple phase boundaries in solid state, in fuel cell is actually very well studied field that people knows how to avoid the formation of unintended voids in solid state device. So I'll show you one successful example how we utilize the void to our advantage, okay? So in the liquid electrolyte, when you make batteries, you put the liquid in. If your anode has a lot of void, because the gravity, the liquid will always penetrate to the voids, okay? Whenever the liquid penetrates to the voids, touch the silicon, the anode, there will be interfacial reactions, SEI formation. So this is one of the reasons that in the liquid electrolyte, silicon until today cannot be commercialized. Forget about what you hear in the media. When they say they use silicon, they use less than 6% of silicon in the graphite cells. Actually, the cell is mostly still graphite, okay? They couldn't solve this interface problem. In the solid state, my student Darren Tang, actually we were inspired by Abik, because Abik said, you know, surely you know, the solid cannot flow into the pores. So if the silicon, when it takes lithium, it's going to volume expand. Why don't we let it expand? But because the electrolyte cannot flow down, so you will have a solid-state lithium-silicon alloy reactions without any interference from the electrolytes. And he's right, because when we use the cheapest possible silicon, actually we can use silicon that recycled from the amorphous silicon solar cells, and you can actually alloy these silicon with lithium in the very fast rate, and you make a functional solid-state batteries with pure silicon, very cheap, no nanostructure, just a very, very low-cost silicon. And this process visualized by cross-cutting SEM and the voltage curve. So you start with a very low-quality silicon, okay? There's a micron silicon with very size, you know, can actually see a lot of voids, you know. And when you lithiate, you know, you drive, using electricity, drive the lithium in, you can see complete densification of this silicon, okay? Now, the magic happens is until today, the science paper has published for 2 years, we could not explain, is when you put the lithium back to the cathode, the pore completely redistribute, and we actually form this kind of columnar pore structure in the silicon, and the macro dimension of this silicon do not change. We have more evidence to show you. After the first cycle, the silicon anode dimension is stable. And because of this discovery, we were able to make average Coulombic efficiency 99.95, and the cell can actually cycle very, very long cycles. And this results actually resulted in a patent that is non-exclusive licensed by LG Energy Solution, who is looking into the solid-state battery commercialization possibility. It's not a fully confirmed yet, but they decided to take this patent just in case. Yeah, so my PhD student, Darren Tan, actually worked on the sodium, but for his PhD, he did some really good work for lithium solid state. So let me summarize by sharing with you where I believe the next decade of energy storage and battery technology will go. I think the society, we should always start with what the society asks us to do. So one of the things I really hope you go away from my talk is to remember batteries is not a disposable. It's a true asset if our society have batteries. We take a lot of energy to mine the elements from the mines, and we should never put these elements back to the waste. Therefore, we will have to figure out battery 100% recyclable and battery build for a very long time, just like the solar panel, is a part of the infrastructure, and we need insurance and infrastructure builders to come and invest. And with that, I think the chemistry or the material science that handle all these, try to mitigate all these questions are here, and one person cannot solve all these problems. So we will need the collaborative team science, and we need companies to come in to play early in the prototyping, because the transition from laboratory research to the production scale, the gap is too big. We will need pilot prototyping, and this is one of the major driving force why I moved to a national laboratory. And I think that it's my responsibility to make sure those technology transfer will be successful. And unlike startup companies who go through many valley of death, National Lab has much more stable fundings, and we are also much more willing to share the results with the public. So I think it's good that we have this dual approach in terms of commercialization. Last but not least, I will finish by saying that a professor's job is, our primary job is students, and the papers and the company become byproduct. And I'm extremely fortunate to, sponsored by many federal and industry partners. And thank you very much for your attention.
Yes, Shirley, this was really a fantastic talk. I think we all agree on this. And we have some time to ask questions. So there are some questions. So there are no questions? Or people are, this was such a clear talk. Yeah, please.
Yeah, thank you for the talk. I guess one thing I'm curious about is with lithium, it's really hard to mine, and so that's where the emphasis with recycling comes from. But with sodium, since we have so much of it, do you think there really still needs to be an emphasis with recycling, or will it be okay to kind of dispose of it since we have salt everywhere?
Yeah, excellent question. I believe that we are in the plastic mess because people believe plastics have no value for recycling. So to handle this challenge, in fact, many universities have started a process for design for recycling. So the goal is to reduce the recycling cost so much that it will just become a natural thing that we will think about recycling. So I think sodium itself, you're right, is very easy to mine, but there's other elements like iron, manganese that in the cathode side, they still need to be recycled. And then I didn't touch a very touchy subject is because a lot of the batteries using fluorinated salts. So I think in the end, to me, the most grand challenge for recycling is how to recycle those highly fluorinated salts for sodium and lithium. Because as you know, the PFAS regulations now is very strict. So but to answer your question, we already thought about that. We want all the students to think about build recycling while you're designing the batteries. Yeah, so sodium batteries, I think, one of the new recycling method is called direct recycling. So we actually don't leach the elements. We actually just use some kind of chemical treatment to repair the particles. And that's still ongoing, the research. Yeah. So,
Thank you so much.
yeah, thank you.
Yeah, Stuart has a question.
Thank you for the great talk. I have a question. So you talked about monovalent ions, lithium and sodium. What about divalent ions? Could you not then increase the charge density?
Mm-hmm. Thank you, Stuart. Yeah, so number one is divalent was the focused topic of the Argonne National Labs hub, J. Caesar, for the last 10 years. And they've made tremendous progress on the magnesium batteries. I think I didn't have the slides here, but if I can derive the Nernst equation for you, so it's the potential is proportional to the free energy over the number of electrons transferred. So unfortunately, based on thermodynamics, the number of electrons, the more electrons you have, the lower the cell voltage will be. So for multivalent batteries, they will have niche applications in areas that is probably not related to mobility, because in the mobility, we have to build the pack of 400 volt or 800 volt. So single cell voltage, we prefer to be very high, and that's why lithium and sodium are considered the top choices. But in the grid storage, I do believe that magnesium batteries or aluminum batteries will become very promising.
Thank you.
Okay, Tony has a question. I have one.
Yeah.
Thanks, Stuart. Thank you, Shirley, for a wonderful talk. What's the preferred solid electrolyte for the sodium solid-state battery?
Very good question. Yep, so I didn't have time today to talk about the sodium solid state. I call them the magic salt. So my preferred chemistry is sodium chloride in between with many other elements, hopefully zirconia, yttrium, magnesium, So the preferred solid state, we should build on that what's already have sodium chloride, so we call it halides. Yeah, I think my group is mostly focusing on the halide-based electrolyte because of the stability, the sodium. And then there's, in Japan and in other parts of the world, a lot of them are working on sulfide-based. And of course, people have not given up on Nasicon. So Nasicon, even though has been around with us for a very long time, never commercialized. But I see recently, I think people find how can we build a Nasicon solid-state battery. So oxides, sulfides, and halides are all moving quite well into possible, demonstration of a real sodium solid-state batteries. Yeah.
Thank you.
Good. I have a short question about the recycling. So you also with sodium, you use PF6. Is there no way to substitute PF6?
Yeah, actually, the other alternative is FSI, sodium FSI. So for some reason, in order to have these high voltage operations, fluorinated salts seem to be the only option right now. In solid state, we don't use that. So for me, the only possibility to move to fluorine-free is actually going solid state. And that's the other big reason, like last week, CATL, BYD, EVE, they all announced the joint development plan for solid state. I think a lot of it is driving by the regulation for the PFAS that the best way to get rid of fluorine is actually going solid state. So we don't have any fluorine in the battery.
Okay, thank you very much.
Yeah.
Okay, so with this, we thank Shirley again, and now the master of the ceremony comes.
Beautifully delivered and very instructive, and it's so exciting to see that the future of batteries is in such great hands. So it's my pleasure to hand over to you the plaque for this Dresselhaus Memorial Lecture. I just have to warn you that this is the heaviest plaque in the world. If this was a battery, it would have to be a lead-acid battery or something like that. So as you will momentarily discover, it's a wonderful plaque, and we'll send it to you, of course. But congratulations on the plaque.